Hey friends, Dr. Borole is here. In the last session, we have seen the arithmetic operations in various number system. Today, we will study the logic gates and the logic operations in digital electronics. The three basic gates are very popular in digital electronics. Those are AND gate, OR gate, and NOT gate. The gates in the logic systems are classified as follows. The basic gates are three: NOT gate, AND gate, and OR gate. The another group is universal gate, under which NAND gate and NOR gates are come, and some derived gates in which exclusive OR and exclusive NOR gates are covered. Whereas this universal gate and derived gates can be implemented using basic gates only. Let us see the first gate. It is a NOT gate. It is also called as inverter. The symbol of the NOT gate is shown here. It consists of single input and single output. Symbol consists of a triangle and bubble at the output. This bubble represents the inversion operation. The input and output both are the logical input, means digital input. So they have only two states. The Boolean expression of the output is given here. Y is equal to A bar or A complement. The truth table which relates the operation of the gate is shown here. Truth table basically lists all the conditions of input and corresponding state of output. Here only single input is there. So 1 bit input results to only two combinations. See here, when input is 0, the output of inverter is complement of it, that is 1. When input is 1, the output will be 0. These two combinations are shown here. When A input is 0, output will be A complement, and when it is 0, output will be 1. When A is 1, output will be 0. The second gate is AND gate. It performs the ANDing operation. It is a logical multiplication. It consists of minimum two inputs to many inputs. Here we will study two input AND gate. The symbol is shown here. It consists of two input A and B, and Y is the output. The truth table of the AND gate with two input is shown here. A and B are the input columns and Y is the output. When A equal to 0 and B is equal to 0, then Y is equal to A and B equal to 0. When A equal to 0, B is equal to 1, output is again 0. When A is equal to 1, B is equal to 0, then output again 0. When A is equal to 1 and B is equal to 1, the output will be 1. In short, we can say the output of this gate is 1 when both the inputs are logic 1, and it remains 0 when any of the input goes low. The two input OR gate is the next gate. The symbol is shown here. This two input OR gate is also called as inclusive OR gate. Minimum number of inputs are 2 and there is a output. The truth table shows here input combination and output combination corresponds to the given input combinations. Let us see here, when A and B both are 0, output Y, A or B equal to 0, and it is represented by the expression Y equal to A or B. This plus sign indicates the ORing operation. When A is equal to 0, B is equal to 1, Y is equal to 1. When A is equal to 1, B is equal to 0, again Y is equal to 1. When A is 1 and B is logic 1, then also Y is equal to 1. We can summarize this operation as the output of the OR gate. So we can summarize the operation of OR gate as the output of the OR gate is always 1 when any of the input is in logic 1 state. The output will be 0 only when both the inputs are 0. Now next gate is the universal gate. This gate can be derived from basic gates only. The two input NAND gate now. Minimum number of inputs are 2 and there is a single output. Multi-input NAND gates are also available. Let us focus on two input NAND gate. It consists of two inputs. The symbol is shown here. This symbol consists of an AND gate symbol with a bubble at the output. So bubble operation represents the inversion. So Y is equal to not AND of A and B. That is called NAND of A and B. The logical symbol is decomposed and shown as an equivalent circuit. It is a combination of AND gate and then followed by an inverter, and therefore AND gate output is inverted at the output. So therefore Boolean expression for NAND gate is not AND. The Boolean expression Y is equal to A dot B complement. The truth table shows the input and output combinations. Let us consider the first row. When both the inputs are 0, Y is equal to 1. When A is 0 and B is 1, so A and B is 0 and complement of it is 1. So therefore A NAND B under this condition is 1. When A is 1, B is 0, then see here A and B is 0 and complement of it, that is Y, equal to 1. So A NAND B in this condition is 1. When both the inputs are 1, say A and B both are 1, the output of the AND gate is 1 and inversion of it, not of it, that is nothing but 1 complement, that is 0. And therefore when both the inputs are 0, A NAND B gives output Y equal to 0. So we can summarize the operation in the truth table in a single line as the output of the NAND gate is logic 0 when both the inputs are in the logic high state. When any of the input is low, the output of the NAND gate is in the logic 1 state. Now let us see the NOR gate. We will focus on two input NOR gate. Here the symbol of the NOR gate is shown. A and B are the inputs and Y is the output. The Boolean expression for the NOR gate is shown as A or B complement. The equivalent circuit of the NOR gate is shown here using basic gates as OR gate followed by NOT gate. So it is OR NOT operation. Let us see the truth table. When A and B both the inputs are 0, then output of the OR gate here in this equivalent circuit is 0 and complement of 0, that is 1, and therefore when both the inputs are 0 in the first row you will get y equal to 1. When A is 0 and B is 1, then OR gate output is logic 1 and complement of it further y is equal to 0. Similarly, when A equal to 1 and B equal to 0, y will be 0. When both the inputs are 1, then y output will be 0. You can check out. When A is 1, B is 1 here, the OR gate output is in the logic 1 state. And complement of it will be available at the output y. So complement of 1 is 0 and therefore when both the inputs are 1, the output will be 0. We can summarize this operation in a single line as the output of NOR gate is always logic 1 when all the inputs are in the low state. Whereas when the inputs are dissimilar, then output y of the NOR gate will be 0. Now let us have exclusive OR gate. The two input exclusive OR gate is shown here. Let us see the symbol. Here A and B are the input and Y is the output. The logical operation takes place here is A exclusive OR B. This plus sign in a circle represents a exclusive OR operation. And the Boolean expression for the output is A exclusive OR B. And it is analogous to Y equal to A bar B or A B bar. This is the operation takes place. Now if you see the truth table, when A is equal to 0 and B is equal to 0, Y will be 0. You can substitute these A and B values in this Boolean expression. So in the first case, if you say A equal to 0 means A bar is equal to 1 and B is equal to 0 means this A bar B is already 0. Then take a next term. A is 0 and B bar is 1. So again A B bar is 0. And therefore, for first combination A equal to 0 and B equal to 0, Y equal to 0. Now consider the second row. In a second row, A is equal to 0 and B is equal to 1. Put these values in this logic expression here for the Y output. A0 means A bar is equal to 1. Whereas B already 1. So A bar B 1 and 1, that gives to output 1. Whereas next term A is 0 and B bar is 0. So A B bar leads to 0. So therefore Y is equal to A bar B, that is equal to 1. Similarly, when A is equal to 1 and B equal to 0, you are getting Y output 1. That can be verified by substituting the value here. Whenever there is a complement sign on a variable, say A bar, then whatever the condition exists in the truth table, you have to use the complement of that bit here as A bar. Here A bar is to be replaced by 1's complement. Here 1 and complement of 1, that is 0. Whereas B is 0, so first term is 0. Second term, A is 1 and B bar is 0's complement means 1. 1 and 1 is 1. And therefore, for third row, when A equal to 1 and B equal to 0, the Y output is 1 for exclusive OR gate. When both the inputs are 1, we will find that this expression of Y will be leading to 0. Therefore, we can summarize the operation of exclusive OR gate as, from the output column, you will see here the output of exclusive OR gate is in logic high state only when both the inputs are dissimilar. When both the inputs are similar, then output will be high. Row number 1 and row number 4. The various application of exclusive OR gates are as follows. It can be used as a magnitude comparator or bit comparator. When bits are similar, the output will be 0. When bits are dissimilar, the output will be 1. It can be used in binary to gray code converter that you will study in digital electronics subject. It can be used as digital adder and subtractor circuit. It can be used to generate the parity of a given digital data and used for checking the parity of the received data. It can be used as a controlled subtractor in the arithmetic logic unit implementation. Here you will see how exclusive OR gate can be used as controlled inverter. Let us consider that there is an input A and there is a output Y, whereas the another input of the exclusive OR gate is a control input. When the control input is in logic 1 state and A is equal to 0, then output will be 1. When A is equal to 1, output will be 0. And you will see that this truth table is just complementing A at output. So, the logic 1 at the control input will enable this inverter and complement of A is available as the output. And that's why exclusive OR gate can be used as controlled inverter. The difference between inclusive OR gate and exclusive OR gate is shown here. What we have already studied, that is listed in a tabular form. The exclusive NOR gate, the name itself indicate it is the NOT operation of exclusive OR. And therefore, if you see the symbol here, there is just a bubble added in the exclusive OR gate that caused the output complement of the exclusive OR gate and made it as exclusive NOR gate. Multi-input exclusive OR gates are also available. The Boolean expression of exclusive NOR gate is shown here. Y is equal to A exclusive OR B complement. It is also shown by the symbol A, and there is a operation symbol as dot in a circle, that is exclusive NOR, and another input B. So A exclusive NOR B, and that is equal to A bar B bar or A B. That is the expression for the output of the exclusive NOR gate. The exclusive NOR gate can be used as even parity generator. It can be used as digital bit comparator, and it can be even parity checker also. Various types of logic gate ICs, those are available in the digital electronics laboratories are for NOT gate inverter, The IC is 7404. Basically, it is LM7404. That is from National Semiconductor. There are many semiconductor companies, those can manufacture all these digital ICs. The 2 input AND gate IC is 7408. The 2 input OR gate IC is 7432. The 2 input NAND gate IC is 7400. The 2 input NOR gate IC is 7402. 2 input exclusive OR gate IC is 7486. And the 2 input exclusive NOR gate IC is 74266. This is all about the logic gates and universal gates and the extended derived gates. Let us have study of Boolean algebra, or also called binary algebra or logical algebra. The Boolean algebra is used to analyze and simplify the digital logic circuits. It is invented by Professor George Boole in year 1854. The symbols in Boolean algebra are usually letters, represents the logic value 0 and 1 only. The Boolean algebra has only logical operations. No arithmetic operations are present in Boolean algebra. Various laws of Boolean algebra are shown in this table. The first law is a commutative law. That is, A dot B is equal to B dot A. Means you can able to change the variable sequence. There will be no effect on the ANDing operation. Dot operation is also called as AND operation. Here A or B is equal to B or A. Plus sign indicates the OR operation here. So variable sequence doesn't affect the operation. That is a commutative law. Associative law. A dot B in bracket dot C. So you can group now A dot in bracket B and C. So grouping the variables in a different order also doesn't affect the operation. Similarly, A or B or C, you can group it as A or in bracket B or C. Then the result remains the same. The distributive law, so A dot B or C is distributed as A and B or A and C. So A will be distributed on B or C. The AND laws, A and 0 is 0 and A and 1 is A. A and A is A and A bar is 0. Means the variable ANDed with its complement is always 0. Simple example, when A is 1, A bar is equal to 0. So 1 and 0 is 0. The OR laws, OR operation laws are listed here. A or 0 is A or 1 is 1, A or A is A, and A or A bar is 1. The inversion law, that is complement law. A complement of complement is the same variable A again. Means if you perform the NOT operation on the variable 2 times, then the variable will not change. So complement of the complement is the same number. The other important laws are A or BC is equal to A or B and A or C. A bar or AB is equal to A bar B. A bar or A B bar is equal to A bar or B bar. A or AB is equal to A. A or A bar B is equal to A or B. These are some laws, those are suitable for simplification of the complex Boolean expression. The next two theorems, those are also used for further simplifications, are De Morgan's theorem. The first De Morgan's theorem is stating that the complement of the product is addition of the complements. Let us understand. Let us see. A and B are the two variables. So complement of the product A and B, that is A dot B complement, is equal to A complement or B complement as per the first De Morgan's theorem, that is addition of the complement. So you will get here A dot B complement is the addition of the complements of the two variable A complement or B complement. So how this logic expression is implemented is shown here. This A and B are the two input. Then A dot B complement is nothing but the NAND operation. Y is equal to AB complement. That is the output of the NAND gate. Now it is equivalent to A and B inverted here by the inverter gives the output A bar and B bar, and then OR it. So A bar or B bar. So Y is equal to A bar or B bar, and that is equivalent to A and B complement. Here these inverters are replaced by two bubbles here and shown as inverted input OR gate. The operation is shown in the truth table. Let us see the variables A and B shown here. Four combinations of A and B are shown. The third column indicates the output of the NAND gate, that is AB complement. Then here the next column indicates A complement and B complement, and the last column indicates the addition of the complement, that is A complement or B complement. So we will see here from the table the column number 3 and column number 6 are same. Means A and B complement is equal to A complement or B complement. And therefore, what De Morgan's theorem says, complement of the product is equal to addition of the complement, is proved from this table. The second De Morgan's theorem is complement of addition or complement of OR operation is product of the complements or AND operation of the complements, because we always say that addition and product or multiplication doesn't exist in Boolean algebra. What exists is addition is nothing but the OR operation, and product is nothing but, or multiplication is nothing but the AND operation. So let us see the OR operation here. A or B complement that can be implemented by using NOR gate. A is input, B is input. So this OR gate provides A or B sub output, and this bubble inverter complements it. So you are getting the output from this NOR gate as Y is equal to A or B complement. The same thing is equivalent to A complement and B complement. So there is an AND operation. So first take the complement of each variable, and the complement can be obtained by using NOT gate. A inverted by inverter we get A complement, then B inverted by this NOT gate you are getting B complement, and ending A complement and B complement you are getting the output Y is equal to A bar and B bar. So these two outputs from NOR gate and this NAND gate are same as per the this De Morgan's second theorem. Here this bubble can be shown in the third figure. Just inverter is pushed inside and bubble is shown at the input. So that is equivalent to inverted input AND gate. Let us verify the second theorem. For that purpose we take the two inputs A and B. We will generate the output A or B bar. That is the output of this NOR gate. That is the first part of your De Morgan's theorem. That is A or B complement. So we got this product here. Then we will get the complement of the variable A and B. And then in the next column we generate the product of the complements. And we will see here for the input combinations from 0, 0, 0, 1, 1, 0 and 1, 1. The third column, that is complement of OR operation A or B complement, and the column A complement and B complement, that is product of the complement. These two columns are exactly same. So therefore we can say that as per the De Morgan's second theorem, complement of OR operation is analogous to the product of OR and operation of the complements. The Boolean expression and the Boolean function. Boolean function is shown as f of a, b, c, d, whereas a, b, c, d are the Boolean variable and f indicates the function. So it is similar to a function representation. We are writing f of x comma y. Here in Boolean expressions, the function is denoted as f of a comma b comma c and so on. And that can be equal to, for example, A or A DC or B C bar. This can be any expression. So, like in mathematics, we can write f of x is equal to x square plus 2x plus 1. So, right side of the expression is a right side of the equation is a expression and left side is called a function. So here also, if the function is in terms of Boolean variable, the expression is nothing but it is a combination operations of Boolean variables. Sometimes the Boolean function f of a, b, c, d can be shown as the letter y. If there are n number of Boolean variables, then the Boolean expression consists of 2 raised to n number of terms. The truth table formation from the given Boolean expression. Let us see y is equal to, suppose given as a or b, c. And how to form the truth table? Make a column for inputs a, b and c. Then make a column for the sub output B and C, and then make a column of output Y is equal to A or BC. There are 8 combinations here for ABC from 0, 0, 0 to 1, 1, 1. So if you see the combination, what is the sub product B and C. See here, B and C, first row, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1, 0 and 0 is 0 again, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 1. Means, whenever you are ANDing, anything AND with 0 is 0. And therefore, B, C AND operation always results to 0 when both the inputs or any of the input is 0. The BC output is logic 1 when both the input B and C are 1. Okay. Let us now take this fourth column and OR it with A. You are getting the output Y is equal to A or BC. So let us see. A or the BC value in the fourth column. 0 or 0 is 0. 0 or 0 is 0 again. The third row, 0 or 0 is 0 again. 0 or this fourth row, 0 or 1 is 1. 1 or 0 is 1. 1 or 0 is 1 again. 1 or 0 is 1 again. And 1 or 1 in the last row is 0. So therefore, the last column output is generated in the truth table. So you can make the truth table for any expression by entering all the input combinations. Then if required, generate the sub combinations given in the expression and then the final output. That is how the truth table will be made. Let us see the use of Boolean algebra to simplify the expression. Let us see the example. Suppose Y output is AB or A bar C or B C. You have to show that this output is equal to AB or A bar C. So simplification can be done by reducing the terms. Let us take the expression here for the Y. We take the right hand side here first. So right hand side is AB or A bar C. As we know, any term multiplied by 1 or ANDed with 1 is the same term. So AB into 1 is AB itself, and 1 can be replaced as C or 1 because anything ORed with 1 is 1. So C or 1 or B or 1 is 1. So we will substitute 1 as C or 1 here, and in the second term we will substitute B or 1 as 1. Okay. This doesn't affect the left hand side expression because C or 1 is 1 and B or 1 is also 1. Now use the distributive law. Here get the product ABC or AB or A bar BC or A bar C. Now from first and third term, make BC common. In the bracket you are getting A from the first term and A bar from the third term. Remaining term kept as it is, that is AB and A bar C. As we know, any variable ORed with its complement is 1. So A or A complement is 1, and therefore replace this bracket as 1. So you will get here BC or AB or A bar C, and if you check this is nothing but the left hand side, and therefore RHS we have proved as LSS, and we have expand this equation here. If you take the left hand side, then you can have a reduction of the variable and you are getting the right hand side. Now another example, if you take AB bar or A or B bar, this is in bracket, and AB bar is equal to AB bar. Let us consider the LHS. Let us apply the De Morgan's theorem. Here, product of the complement is the OR operation of the complement. So, A B bar is equal to A bar or B bar. So, here we will replace it A bar or B bar. Second De Morgan's theorem is applied here. Complement of OR operation is product of complement. So, A or B bar here will be replaced by A bar and B bar, and the next term AB bar is as it is. Now distribute this term AB bar on this bracket. So it gives you A bar A, B bar. Second term B bar A, B bar. Then third term A bar B bar and A B bar. Whereas B bar is the product, that is B bar only. And therefore, here this last term B bar and B bar is equal to B. So LHS becomes A bar AB or B bar A or A bar B bar A. But we know the variable and its complement ANDing operation of A and A complement is 0. And therefore here you will see A and A complement will be replaced by 0. So this 0 and B bar is 0. B bar A as it is. And the last term A complement and A again 0. And therefore it comes out to be B bar A. And therefore by using these two De Morgan's theorem, we have simplified the expression to y is equal to B bar A. So this simplification leads to reduction of the variable. You will see here, to implement this particular operation, if you consider left hand side, you will have two variable A and B. So you will need one gate, that is a NAND gate, for implementing A and B bar. Secondly, for second bracket, you will get a NOR gate for implementing A or B complement. And then you need a third 3-input AND gate to combine the output of these three terms. Additional inverter is required for getting the complement of B bar, and one AND gate is required to implement the product AB bar. So 1, 2, 3 and 4 gates and additional 3-input AND gate is required to implement the left hand side. Whereas if this is simplified to AB bar only, then you can have one inverter that inverts B, getting B complement, and one 2-input NAND gate. So 5 gates are replaced by only 2 gates, and that will reduce and simplifies the hardware. The other example, student can go through it and use the Boolean expressions and Boolean theorems simplification using De Morgan's theorem and Boolean algebra rules and make a practice. Some of the example solved here. You can go through it and check out. The examples of Boolean theorem are shown here. Let us say the variable expression is y is equal to a bar b or ab bar complement. So using the first theorem, the complement of OR operation is equal to the product of complements. So x or y complement is equal to x complement and y complement. So apply this to this expression. So first this operation OR operation is shown here, that plus sign will be replaced by dot and break this bar, complement bar. So you are getting a bar b complement and a b bar complement. Now use the another theorem of De Morgan's. The complement of product is the OR operation of complements. So you will see here the first term, it is a complement of product a bar b, and second term is a complement of the product a b bar. So apply this here. So this complement operation converted to OR operation. So what it becomes? A complement of complement and b complement. So here a complement of complement or b complement, and AND operation is now converted to OR operation. Now take the second term. In second bracket, you are getting break this complement top bar. So it becomes a complement. Now replace the products here, a b complement as a complement or b complement of complement. So b complement of complement. Now simplify further. Complement of complement is the same variable. So a complement of complement is a itself, then b bar itself, then a bar here, and b double bar means b complement of complement is b, and therefore we have a simplified expression here. Similarly, you can go through this example and apply the De Morgan's theorem. First, two brackets are separated by taking the De Morgan's theorem, applying the De Morgan's theorem. Here, the product operation of the two bracket will be converted to OR operation and the complement bar will be divided in two parts. Now here, to individual term, you have to apply the De Morgan's theorem again. Here the complement of OR operation results to product of complements. So again this OR sign will be replaced by a product dot and break this complement bar here. So it becomes a bar, b complement of complements is b double bar, or c bar and d double bar. So ultimately b complement of complement is the same variable. So a bar b and c bar d. That will be the simplified expression. So by using Boolean expression and De Morgan's theorem, you can simplify the Boolean expressions. There is another type of question that comes in your examination. They will give you the circuit and you have to write the expression for the output. So let us suppose this is the circuit given. There is an AND gate having two inputs A and B, and there is a third input that is ORed with the intermediate output. the intermediate output, if not marked, you have to mark it as say y1. Then the intermediate output of gate 2 is marked as y2, and then the final output of the inverter is marked as y. From this diagram, you have to write the expression for final output. The simplest way is to write the individual expression for y1, y2, and then you combine the expression of y1 and y2 and inputs to get the y output. Let us see here in this example, y1 is nothing but a and b. So we have written y1 is a and b. What is y2? y2 is c or y1. y1 is a and b. So c or a and b is y2. And what is y? Y is complement of y2. So y2's complement a or a and b or c complement is y. And this is the expression given by the circuit as a Boolean expression. So this is one way. From circuit we have written the Boolean expression. Sometimes they will give you the Boolean expression and you need to implement this Boolean expression by the digital electronic building blocks, means using digital electronic gates. Let us see. Suppose the Boolean expression given is y is equal to a and b, or b and c, or a bar and b bar. Now there are three product terms here and those are ORed. So 2 input AND gate is required for first term, second 2 input AND gate is required for second term, and third input AND gate is required for third term. So let us take the first term a and b as input to the AND gate, and you generate the output y is equal to ab. Then second term b and c are the input for the second 2 input AND gate, and y is equal to y2 is equal to b and c here. Whereas a bar and b bar are the complements. So take a and b, then use two inverters, you will get a bar and b bar, and then add a bar and b bar. So therefore y3 is equal to a bar and b bar. Now these three outputs are OR together, and that is using 3 input OR gate here. So we are getting the output y is equal to ab or bc or a bar b bar. Here the same inputs, say a and b connected to gate 1, b input is again connected to gate 2, and c input is connected to gate 2. Again a and b inputs are taken, they are complemented and connected to the third input gate, and the three outputs are ORed by using 3 input OR gate, and you are getting the Boolean expression. So whatever the Boolean expression given here, that can be implemented by using digital electronic gate. Now to this digital electronic gate, if you change the combination of input A, B and C, you are getting at the output Y, that is AB or BC or A bar, B bar. Students are expected and given the exercise as write the truth table for this Y. So how to make a truth table we have already studied. Make 3 columns for input A, B, C. Then 3 columns for output Y1, Y2, Y3, and the final column Y. And verify by changing the combination of inputs A, B, C, how the sub outputs Y1, Y2, Y3 changes, and then how the final output is generated in the truth table. Now once the truth table is prepared, and if you build this circuit in digital electronics lab and so set this combination of ABC inputs, then you can verify that whatever the combination you get in the truth table, this circuit generates the same result. Here three exercises are given to the student. They can solve these exercises at home. So from these exercises, the expressions given here, you have to implement the circuit using logic gate and make a truth table. So friend, today we will stop here. Till then, bye bye.